So here in these mechanisms, the processes, we are not being very specific about whether we are talking about MJOs or easterly decaying or easterly intensifying events. We are just talking about the processes of organizing convection and what are the ocean and atmosphere processes involved in this. So looking at the buildup of SSD again, going from composite day 0 to few pentads before and few pentads after, you see this buildup of sea surface temperatures in the far western Pacific Ocean and the western or central Indian Ocean, and you can see the similarity in the two figures, almost the same, and you see processes are almost the same as well. We are looking at the upper tropospheric humidity and wind speeds and OLR, rainfall, etc. And you can follow slowly here. You are looking at wind speed in black. As the SSD has to warm, wind speeds weaken. Not so much here, but much more clear here, and that reduces the latent heat loss and allows the SSDs to warm and ocean heat content to build up. And there is the dry phase, so rainfall is less here in the warming phase ahead of the buildup of the upper tropospheric humidity, and then when convection happens on day 0, you have this sharp drop in OLR, and then the OLR begins to build up again in the following few pentads. Okay, so that's the instability mechanism that we already talked about, and looks almost the same in the central eastern Indian Ocean average over the deep tropical Indian Ocean. Again, you can see the rainfall low during, so rainfall is shown here in, the scale here is in millimeter per day, which should be this one, and wind speeds low here, and then convection kicks up the winds because convective phase is a perturbation phase associated with wind speeds, heat loss from the surface, cyclonic circulation, upwelling, entrainment, cooling, and so on. Upper tropospheric humidity builds up as the SSDs warm. OLR drops as the convection happens here. A little bit of a phase lag, but nonetheless you can see that the rainfall peaks and then drops off. OLR drops and then picks up again. Okay, very coherent processes, but again, these are not always exactly the same way, but each event can be occurring this way. We didn't talk much about the ocean processes themselves, but the SSDs that we are talking about is essentially in the well-mixed layer that we talked about. So the surface temperatures are mixed up, and then you have the thermocline, and then you have surface salinity that's mixed up, and you have the halocline, and we have the density which is got mixed up uniform density, and then you have the pycnocline or the density gradient. Of course, when you have typical conditions where there is a lot of freshwater forcing, like the Western Pacific, where in fact this barrier layer was first defined by Lucas and Lindstrom, which is kind of a classic paper. There were some ideas about this structure before by Stuart Godfrey as well. But you can see that here, because of the surface freshwater forcing and other mechanisms of subducting the freshwater below the surface, you have a fairly uniform isothermal layer that is much deeper than the isohaline layer. Then the density layer is also different than here. So you end up with this temperature gradient, but a very different salinity stratification. This is critical because when entrainment happens, in this case, if this is the mixed layer here or the isothermal layer or the isopycnal layer, then when entrainment happens here, you will be mixing water that's similar density, so you will not cool the surface. This is why this is called a barrier layer. It kind of decouples the dynamics of the mixed layer from the thermodynamics of the entrainment mixing, whereas here when you have entrainment mixing, you're going to mix the colder waters and going to end up cooling the surface. So this is important to remember and plays a critical role in terms of the memory of the system, etc. The destabilization here can be seen in terms of SSTs, where the buildup phase is the destabilizing phase, buildup of the moist static energy gradient, the convective available potential energy. Then you have the convective phase, wind speeds kick up, heat loss increases, and entrainment, etc. And you have cooling of the sea surface temperature, and then you have restoration or the reorganization of the SSTs ahead to make the convection move or not, based on whether it's MJO or eastern decaying or eastern intensifying. If you look at the profiles, you have the moisture profile, you have the dotted line, which is the background profile, so you make sure you read it properly. So moisture change during the phases defined with respect to SST cycle. So the atmospheric temperature is red, used as reference for how the atmospheric temperature and moisture change during these phases defined with respect to SST. Blue in the middle. Change of cloud conditions and associated wind field and heating changes are indicated in the bottom. So you can see that there is during the loading phase you have drying, but moistening at the surface, and as you head towards destabilization, the upper atmosphere is cool because there is radiative cooling, but there is warming at the surface because of the latent heat loss building up the moisture and atmospheric profile. And then during the convective phase you are going to spend the moisture and then stabilize the air column, because you're going to mix up and remove the instability that is built up during the destabilization phase, and then you are back to restoration with slight drying and slight warming. So here is weak winds, high radiation, no clouds, SST is warming. During convective phase you have stronger currents, winds causing latent heat loss, SST cooling, radiation is reduced but latent heat loss is increased, there is rainfall, freshening of the surface, and then again you begin to weaken the winds and evaporation decreases, and then you begin to warm the SSTs again. So looking at CAPE, the convectively available potential energy in terms of joules per kilogram, you can see the time series of the first ISV event during the Toga core that was observed during the intense observing period, with lots of ships and aircrafts and lots of people excited about it. So here is again the destabilization phase, buildup of the CAPE, convection removes the instability, converts potential energy into kinetic energy, and then into the restoring phase. Okay, so look at the details of the convective phase in the next podcast, but just listen again and look at the figures again. It's very simple. The entire ocean atmosphere process is involved. We are mostly talking about surface exchange because at MJO time scale the thermocline movement is involved, and there are lots of papers talking about how that happens, because MJO's wind anomalies can send off Kelvin waves in the ocean as well, which can go ahead and change the thermocline and affect sea surface temperature budgets, which do include the impact of the thermocline movement on the surface heat budget. But we are not getting into the oceanic processes here. The chapters by Billy Kessler and Harry Hendon that I mentioned from Intraseasonal Variability book by Bill Lau and Dwayne Walliser has excellent details of these ocean processes. Okay.